Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about the module Maxwell's Equations 1 from the paper Electromagnetic Theory. From this module, you may get to know about the following: the modification in the equations of electricity and magnetism for time-varying fields. Then, Maxwell's equations in vacuum and the modifications needed in a medium. After that, we will be introducing the concept of potentials, the first step towards the solution of the Maxwell's equations. We have studied the subject of electricity and magnetism in great detail in our undergraduate classes. The basic laws of electricity and magnetism, which you learned in the undergraduate courses, are summarized in the following equations: the Coulomb's law, the Ampere's circuital law, the Faraday's law of electromagnetic induction, and the absence of free magnetic monopoles. These equations obviously need some elaboration. First of all, these quantities, that is the electric field vector E, the magnetic field induction vector B, and the current density vector J, and the charge density rho are fields, that is, they are functions of space and time. So the electric field is a function of position vector x and time t. The magnetic field induction vector is a function of position vector x and time t. And so are the other quantities. These are the different forms of the equation of electricity and magnetism. You have also studied all these equations in their integral forms as well. The basic laws. So we begin the discussion of electrodynamics by first of all discussing the basic laws of electricity and magnetism in the differential form, which have been defined in the free space. That means that the medium that we are using for defining or discussing these laws of electricity and magnetism is free space, where the velocity of light is c and is equal to 3 × 10⁸ meters per second. So the first law that we would be discussing over here is the Coulomb's law, which basically tells us that the divergence of the electric field is equal to rho upon epsilon naught, where rho is the volume charge density and epsilon naught is the permittivity of free space, electrical permittivity of free space. The second law that we discuss over here is the Ampere's circuital law, and which is given as the curl of the magnetic field induction vector B is equal to mu naught times the current density J, where mu naught is the magnetic permeability of free space. The third law that we discuss over here is the Faraday's law of electromagnetic induction, which is defined as the curl of the electric field plus the time variation of the magnetic field induction vector, that is del cross E vector plus del B vector by del T is equal to 0. And the fourth law that we discuss over here is the absence of free magnetic poles, that is the absence of magnetic monopoles, which is given by the equation that the divergence of the magnetic field induction vector B is equal to 0. So the first law actually, that is the Coulomb's law, by using the Gauss's divergence theorem, we can write the Coulomb's law in this differential form that we have just mentioned. Similarly, we can use the Ampere's circuital law, and we can then use the Stokes theorem to write the Ampere's circuital law in the present differential form. In a similar manner, we have also utilized different relations to write the Faraday's law of electromagnetic induction in this differential form, because otherwise, if you can recollect, Faraday's law of electromagnetic induction basically states that the induced EMF is equal to the negative of the time variation of the magnetic flux. So using the definition of magnetic flux and putting the value of magnetic field induction vector, and then also utilizing the definition of the electromotive force and using the electric field in place of that, we can derive the present form that we have written over here. And finally, the last equation is nothing but the Gauss's divergence theorem in magnetostatics. So just like Coulomb's law is the Gauss's divergence theorem in electrostatics, the absence of the magnetic monopoles is simply the Gauss's divergence theorem in magnetostatics. Problem with the equations. Now let us look at what are the problems with the equations that we were just talking about. The above equations are derived from steady state phenomena and may, in fact, they do need modifications for time varying phenomena. They are inconsistent as they stand and violate the law of charge conservation. The equation of continuity, which embodies the law of conservation of charge, given by the divergence of the current density vector J plus the partial time derivative of the charge density rho is equal to 0. For steady state phenomena, the partial derivative with respect to time of the charge density rho goes to 0, and we get the divergence of the current density J as equal to 0. And from the Ampere's law, which implies taking divergence on both sides, that the divergence of the current density vector J is equal to 0. Thus, the above equation is consistent with charge conservation for steady state, but not consistent for time varying fields where the partial derivative of the charge density with respect to time does not go to 0. Maxwell found the way out by rewriting the continuity equation by using the Coulomb's law. Displacement current. Now, if we look at the continuity equation, which embodies the law of conservation of charge, and if we replace for the volume charge density using the Coulomb's law and rewrite the volume charge density in terms of the electric field, then the continuity equation can be rewritten as divergence of bracket open current density J plus epsilon naught times del vector E by del T bracket close is equal to 0, where epsilon naught is the electrical permittivity of free space and del vector E by del T denotes the time variation of the electric field. So now, in order to ensure that the Ampere circuital law not only is valid for the static fields and static phenomena, but is also valid for the time varying fields and the time varying phenomena, we modify the definition of the current density given in the original form of the Ampere circuital law with what we have derived over here from the continuity equation by using the Coulomb's law. So the current density J can then be replaced by two terms, that is current density J plus epsilon naught times del electric field vector E by del T, and then the Ampere circuital law is modified to the curl of the magnetic field induction vector B is equal to mu naught times bracket open current density J plus epsilon naught times del by del T of electric field vector E bracket close. Here the additional term epsilon naught del by del T of electric field vector E, that is the time variation of the electric field vector E, is called the displacement current. Though this may appear to be a small modification, but the fact is that it has very profound consequences. And these consequences, as we move through this course, we will ourselves see. So this was one of the main contributions that Maxwell made to the four equations that we have discussed earlier, wherein he modified the Ampere circuital law to accommodate not only static phenomena but also to accommodate time varying phenomena and time varying fields. So in this manner, we can now define the new set of four equations which are called the Maxwell's equations. Maxwell's equations in vacuum. Having made the modification in Ampere's circuital law, we can now rewrite the Maxwell's equation in vacuum, that is in free space, which not only caters to the static phenomena and the static fields, but also to time varying phenomena and time varying fields. So these equations can now be written as the first equation, which is Gauss's divergence theorem in electrostatics, and now obviously is valid for even time varying fields. The divergence of E is equal to the volume charge density by epsilon naught, where E is the electric field and the volume charge density is denoted by rho, and epsilon naught is the electrical permittivity of free space. Ampere's circuital law can now be rewritten as the second of Maxwell's equations, which is the curl of the magnetic field induction vector B is equal to mu naught times bracket open the current density vector J plus epsilon naught times del by del T of the electric field vector E bracket close, where epsilon naught del by del T of the electric field vector E is the displacement current given by the vector D. The third of the Maxwell's equation is the Faraday's law of electromagnetic induction and is written as the curl of the electric field vector E plus the time variation del by del T of the magnetic field induction vector B is equal to 0. And the fourth of the Maxwell's equation, which is Gauss's divergence theorem in magnetostatics, is that the divergence of the magnetic field induction vector B is equal to 0. The highlight of these four equations that Maxwell wrote are that they provide the complete description of phenomena involving electromagnetic fields and charged particles. Now, in order to further elaborate upon these equations and to make these equations more comprehensive, we need to include the Lorentz force equation, which is given by that the force acting on a charged particle in the presence of an electric and magnetic field is given by vector F is equal to Q times bracket open electric field vector E plus velocity vector V cross magnetic field induction vector B bracket close, where Q is the charge which is moving under the influence of the electric and the magnetic field, and the vector F gives the force due to the electric and the magnetic field vectors having charge Q. The other equation that we need to consider is the Newton's law, which basically states that the force vector F is equal to the time variation of the momentum vector P. That is, F vector is equal to d by dt of the momentum vector P. Maxwell's equations in matter. So the Maxwell's equations that we have defined above for vacuum or free space are correct and apply everywhere. However, what is important to note over here is the fact that when we look at materials, then materials are subject to electric and magnetic polarizations. Now, what we would typically like is to have equations which involve only free charges and free currents. However, when we consider the electric polarization leads to bound charges, where rho subscript B, which denotes the bound charge density, is equal to minus divergence of the polarization vector P, where the vector P is the electric polarization vector. Similarly, the magnetization also leads to bound current, where the bound current density vector J subscript B is equal to curl of the magnetization vector M. Now, another important thing over here is that change in polarization due to time dependence further leads to bound currents. So, if we want to look at the current flowing through a surface area dA, then the current element di is equal to del by del T of rho subscript B del by del T of sigma subscript B times dA perpendicular, and this is equal to d capital P by dt times dA perpendicular, where sigma subscript b is the bound surface charge density, dA perpendicular is the surface area vector perpendicular to the surface, and capital P is the electric polarization. So here the current that we have discussed, that is the current element dI, is due to the bound charge density. Similarly, the current density vector J due to the electric polarization is given by vector J subscript P is equal to del by del T of vector P, that is the time variation of the electric polarization vector, so that when we take the divergence of the current density due to the electric polarization, that is del dot vector J subscript P is equal to del by del T of divergence of the electric polarization vector P. And from the continuity equation, we know that the divergence of the electric polarization vector is nothing but the volume charge density of the bound charges. So the divergence of the current density vector J subscript P, that is due to the electric polarization, is equal to minus of time variation of the volume charge density of the bound charges, that is minus del by del T of rho subscript B. Thus, the total charge density due to both free as well as the bound charge densities is given by rho, that is the total charge density, is equal to rho subscript F plus rho subscript B, where rho subscript F is the volume charge density due to free charges and rho subscript B is the volume charge density due to the bound charges, and this is equal to rho subscript F minus del dot P vector, that is volume charge density due to the free charges minus divergence of the electric field polarization vector. Maxwell's equations in matter. Just like we had defined the total charge density as the sum of the free and the bound charge densities, so the relation for the total current density vector J is equal to vector J subscript F plus vector J subscript B plus vector J subscript P, where vector J subscript F is the current density due to free charges, vector J subscript B is the current density due to bound charges, and vector J subscript P is the current density due to electric polarization. So the current density due to bound charges is given by the curl of the magnetization vector M, while the current density due to electric polarization is given by the time variation of the electric field polarization vector P. Hence, the Gauss's law, which is the first of the Maxwell's equation, now takes the form divergence of the electric field vector E is equal to 1 upon epsilon naught times bracket open rho subscript F minus divergence of the electric field polarization vector P bracket close, or the divergence of the electric field displacement vector D is equal to, where rho subscript F is the volume charge density due to free charges, and the electric field displacement vector D is defined as epsilon naught times the electric field vector E plus the polarization vector P. Similarly, the modified Ampere's law using the above definition of the current density, which includes both free and the bound current densities, becomes the curl of the magnetic field induction vector B is equal to mu naught times bracket open current density vector subscript F plus curl of the magnetization vector M bracket close plus mu naught times the time variation of the electric displacement vector D, where the current density vector F subscript F is the current density due to free charges, the curl of the magnetization vector M denotes the current density due to the bound charges, and the last term involving the electric displacement vector, the time variation of the electric displacement vector, denotes the current density due to the electric polarization. So this can be rewritten as curl of the magnetic field vector H is equal to the current density vector J subscript F plus time variation of the electric displacement vector D, where the magnetic field intensity vector H is equal to 1 upon mu naught times the magnetic field induction vector B minus the magnetization vector M. One can also see that the other two of the Maxwell's equations are not affected by this change of definition of the charge density and the current density, as they do not contain any sources. Here, the electric displacement vector D and the magnetic field intensity vector H are called auxiliary fields because they are used to absorb the effect of bound charges and currents. Constitutive relations. Now let us write down the Maxwell's equations in matter in terms of the free charges and the free current densities. So the first of the Maxwell's equation, which is essentially the Gauss's law, is modified as the divergence of the electric displacement vector D is equal to free volume charge density rho subscript F. The second of the Maxwell's equation is then written as the curl of the magnetic field intensity vector H is equal to the current density due to free charges, that is vector J subscript F, plus the time variation of the electric displacement vector D, that is del vector D by del T. The third of the Maxwell's equation can be written as the curl of the electric field vector E plus the time variation of the magnetic field induction vector B is equal to 0. And the fourth of the Maxwell's equation can be written as the divergence of the magnetic field induction vector B is equal to 0. Here we have introduced two more auxiliary relations, which are the constitutive relations and which relate the electric displacement vector to the electric field vector E and the magnetic field intensity vector H to the magnetic field induction vector B. Now if we look at linear materials, and in most cases the materials are linear, that means their properties are linear, or in other words the various terms or the physical parameters occur in the first power. So for all such materials that are linear, the electric polarization vector P is defined as epsilon naught times xi subscript E times the electric field vector E, where epsilon naught is the electric permittivity of free space, xi subscript E is the electric susceptibility. Similarly, the magnetization vector M is defined as xi subscript M times the magnetic field intensity vector H, where xi subscript M is the magnetic susceptibility. And thus, we can write down the relation for the electric displacement vector D as being equal to epsilon naught times the electric field vector E plus the polarization vector P. And using the definition of the polarization vector as defined above, we can rewrite the equation for the electric displacement vector as epsilon naught times bracket open 1 plus xi subscript E bracket close whole times the electric field vector E, and this can be then further written as electric displacement vector D is equal to epsilon times electric field vector E, where epsilon is equal to epsilon naught times bracket open 1 plus xi subscript E bracket close, where epsilon is called the permittivity, the electrical permittivity of the material medium, epsilon naught is the electrical permittivity of free space, and xi E is the electric susceptibility. And the quantity epsilon by epsilon naught, which is equal to 1 plus xi subscript E, is called the dielectric constant of the material and is denoted by the term kappa. Constitutive relations. Just like we have defined the constitutive relations for the electric field and we have defined the electric displacement vector in terms of the electric field vector, similarly now we define the constitutive relations for the magnetic field. So the magnetic field induction vector B is equal to mu naught times bracket open magnetic field intensity vector H plus magnetization vector M bracket close, and this is equal to mu naught times 1 plus xi under subscript M bracket close whole times the magnetic field intensity vector H. Then the magnetic field induction vector B can be written as being equal to mu times the magnetic field intensity vector H, where mu is equal to mu naught times bracket open 1 plus xi subscript M bracket close, and this is equal to mu naught times mu subscript R, where mu subscript R is 1 plus xi subscript M, where the constant xi subscript M is the magnetic susceptibility of the material. Mu is called the magnetic permeability of the material. Mu naught is the magnetic permeability of free space. And mu subscript R is called the relative permeability of the material medium. Once again, considering linear materials only, that means materials for which these various physical parameters and quantities occur in the first power, we can write down the Maxwell's equations as the divergence of the electric field E is equal to the volume charge density rho upon epsilon. The curl of the magnetic field induction vector B is equal to mu times bracket open the current density J plus epsilon times the time variation of the electric field vector bracket close. Here mu is the magnetic permeability of the material medium and epsilon is the electric permittivity of the material medium, and vector J is the current density. The curl of the electric field E plus divergence of the magnetic field induction vector B is equal to 0. So if we compare these equations, that is the Maxwell's equations that we have obtained above for linear materials in material medium with the Maxwell's equation that occur in vacuum or free space, we see that by simply replacing epsilon naught and mu naught, that is the electrical permittivity of free space and magnetic permeability of free space, with epsilon and mu, that is the electric permittivity of the material medium and the magnetic permeability of the material medium, we can again get the Maxwell's equation in the same form. Scalar and vector potentials. Now, once we have defined the Maxwell's equation in free space and the Maxwell's equation in a material medium, we have also talked about the total charge density and the total current density as in terms of the free charge density and the bound charge density, and the free current density and the current density due to bound charges and those due to the polarization charges. Now let us move further to solve these Maxwell's equations. One of the most important aspects of dealing with any problem in physics is to simplify the equations, because the more the number of equations, the more the number of variable parameters that are required to solve it, the more complicated the solution is. So what our effort over here is to basically see if we can reduce the Maxwell's equation from the existing 4 equations to a lesser number of equations, and when we attempt to do that, to also ensure that the equations that we get thereof are uncoupled, that means have only one variable parameter. So now let us look at these equations. Right now we have a set of 4 coupled partial differential equations. 2 of them are scalar and 2 of them are vector equations for 2 unknown vectors, which are the electric field vector E and the magnetic field induction vector B. So as a first step, what we do is we reduce the number of equations to a smaller number by introducing potentials. Now if we look at the fourth of the Maxwell's equation, that is the divergence of the magnetic field induction vector B is equal to 0, then we know from our knowledge of divergence that if the divergence of any vector is 0, then that vector can be written as the curl of another vector, because the divergence of the curl of a vector quantity will always give a 0. So we can define the magnetic field induction vector B as being the curl of another vector quantity A, where vector A, which is a function of the position vector x and the time t, is called the vector potential. Now let us look at the third of the Maxwell's equation, which is that the curl of the electric field vector E plus the time variation of the magnetic field induction vector B is equal to 0. In this equation, when we substitute for the value of the magnetic field induction vector in terms of the vector potential, then the equation turns out to be curl of the electric field vector E plus del by del t of curl of the vector potential A is equal to 0. Since the del operator is independent of time, therefore interchanging the order of differentiation between the partial time derivative and the del operator in the second term involving the vector potential will not lead to any different result. Hence, we can rewrite this equation as curl of bracket open electric field vector E plus partial time derivative of the vector potential A bracket close is equal to 0. Now we know that if the curl of a vector is 0, then that vector quantity can be written as the gradient of a scalar potential. So let us write the vector quantity E plus partial time derivative of the vector potential A as the gradient of a scalar function, which is given by minus of gradient of the scalar potential phi. So rewriting this equation, we get the electric field as being given by the electric field vector E is equal to minus of the gradient of the scalar potential phi minus the partial time derivative of the vector potential A, where the scalar potential phi is also a function of the position vector x and the time t. From this discussion, we can see that given any scalar and vector potentials, the two homogeneous equations are automatically satisfied. Scalar and vector potentials. Now let us try to find out the dynamical behavior of the electromagnetic fields which are given by or determined by the other two of the Maxwell's equations. First, what we have to do is that we substitute the values of the electric field vector E and the magnetic field induction vector B in terms of the scalar potential phi and the vector potential A. Then these equations can be rewritten as the Laplacian operator acting on the scalar potential phi, that is del 2 phi, plus the partial time derivative of the divergence of the vector potential A is equal to minus of the volume charge density rho by epsilon naught. And the other of the Maxwell's equation, that is the last of the Maxwell's equation, can be written as the Laplacian acting on the vector potential A minus mu naught times epsilon naught times the double partial derivative with respect to time of the vector potential A minus del operator acting on bracket open divergence of the vector potential A plus mu naught times epsilon naught times partial time derivative of the scalar potential phi bracket close is equal to minus of mu naught times the current density vector J. Here the quantity mu naught times epsilon naught whole to the power minus half has the dimensions of velocity, and one sees that it typically turns out to be the velocity of light in vacuum or free space. Hence is often denoted by C. So the above equations can be rewritten as Laplacian operator acting on the scalar potential phi plus partial time derivative of the divergence of the vector potential A is equal to minus of the total volume charge density rho upon epsilon naught, and the second equation can be rewritten as Laplacian operator acting on the vector potential A minus 1 upon c square times double partial time derivative of the vector potential A minus divergence of bracket open divergence of the vector potential A plus 1 by c square times partial time derivative of the scalar potential phi bracket close is equal to minus mu naught times the total current density vector J. So what we have seen is that by using the definition of the scalar and the vector potential and replacing this in terms of the electric field and the magnetic field induction vectors, we have succeeded in reducing 4 of the Maxwell's equations into 2 equations which involve the scalar and the vector potentials only. However, in the process what we have are second order differential equations which are coupled, as these equations involve both the scalar and the vector potential. So students, let us now summarize what we have learned in this module. Firstly, it was explained that the Ampere's law as it stands is inconsistent with the equation of continuity which expresses the law of conservation of charge. Next, we learned how Maxwell modified the Ampere's circuital law for time varying phenomena to make it consistent with the continuity equation and also with the conservation of charge, that is the law of conservation of charge. Then the Maxwell's equations were written in complete generality in vacuum as well as in a medium by taking the polarization and the magnetization into account. The concept of scalar and vector potentials was introduced. The introduction of potentials, that is both scalar and vector potentials, simplifies the equations to some extent and provides the first step in an effort to solve Maxwell's inhomogeneous equations. Thank you.